Hi, this is us going out now. Hi, folks. I'm not using the right mic. Okay, hold on.
No.
No, it's a simple problem. My mic is sitting on the surface of my desk, and I don't have the noodly bit attached. Does that sound better?
Yes.
Okay.
Yeah.
Hi, everyone.
I was I was just explaining how to propagate plants. So
And it was
I
making you
found I was
happy.
I was telling Pamela I found I'll move out of the way. So I found there's an apple tree growing in a corner of my property that is like wild. But I ate apples from it last year, so I know that it does produce apples. And but I like how hardy it was. Like it grew up in the middle of a dense forest. Like I figured like a logger threw a apple down 40 years ago, and it's
Yeah.
making this little apple tree. So I went up and grabbed a whole bunch of cuttings from it, and I'm going to try and propagate a whole bunch of versions of this apple tree. And there's a fuchsia. I really like outdoor fuchsia, hardy fuchsia. I love fuchsias. I think they're like my favorite flower at this point.
Really?
And so there was a house that was being demolished right beside a friend of mine's house, and they're like, "Why don't you come on by and see if you can
Oh,
save
yeah.
anything?"
Yeah, we have one of those in
And
our yard. I love it.
yeah. And so there was a fuchsia, and it's an outside fuchsia. It had gone through minus 18 Celsius. No one had watered it. It had been by this abandoned house for 10 years, so nobody was taking care of it. I figured, okay, that sounds like a good fuchsia.
Yeah.
And so I took apparently your volume is low. So I went and grabbed a whole bunch of cuttings off of it and put them all in my, propagated them all, and they all took. So
Oh,
like
wow.
normally I see like a maybe 20% take, and this one every single one took. And in fact, it's only been about a month and some of them are already producing flowers. Like these tiny little cuttings are producing these tiny little fuchsia flowers. It's adorable.
Oh,
So
man.
let me know if you need it. If anybody needs a hardy fuchsia, have I got a lot of them?
Yeah, I have a fuchsia. I thought it was called a bleeding heart plant, but it's apparently a bleeding heart fuchsia is what it is.
I mean, there are bleeding hearts.
Then it's a bleed. I
So
have no
bleeding
idea.
heart makes these little. They look like little hearts, and they kind of
Yeah,
hang below the leaves.
but doesn't
And
fuchsia make plants that have flowers that hang below the leaves?
sort of a fuchsia will put them sort of out at the end of their branches,
Okay.
and they kind of look like alien monsters,
Mm-hmm.
while the bleeding hearts do look like little purses that are hanging below the branch. So
Yeah,
you
I guess I have a bleeding heart
probably,
plant, not a fuchsia plant.
yeah, and a
Okay.
bleeding heart likes shade and
Oh yeah, yeah.
yeah, but it can handle being
Fuchsia,
outside. It
fuchsias
likes
need
to be.
sunlight.
No, fuchsias want to be in the shade too.
Okay, I need
Yeah,
to get some fuchsia plants.
yeah. Welcome to Botany Cast. Yeah, fuchsias are the best. Fuchsias are the absolute best. And so you take a fuchsia, you grow it in the summer because most fuchsias can't handle cold weather.
Uh huh.
And then at the end of the season, you hack it back almost to the root. You put it in your garage, and you just keep it moist over the winter, and it's fine. And then you bring it out in spring, and it sends up all these new roots. And you put it in a pot, and away you go. And it just makes the best flowers. You just Google
That's
search what a
awesome.
fuchsia looks like. So apparently, I'm still louder than you are.
All right, I'm going to turn you down this time.
Yeah, I'm the offender. Fuchsia Fest 2022. Beautiful observatory. So another thing that's interesting is there's a new show on Netflix called Sea Wolf Island,
Okay,
and it's all about Vancouver Island wildlife. So
that's
they
awesome.
follow our sea wolves, they follow a bunch of sea otters, they follow some eagles, they follow bears, humpback whales, orcas, the great herring
Those things are scary.
madness every spring. And so if you wanted to sort of see what life is like here on Vancouver Island, wildlife is like, it's fairly accurate. It felt right. There was like a few tiny little things where, like you see eagles fishing, but our experience of eagles is at the dump, right? fighting a bear over a dirty diaper. So, right. But
I love that.
definitely watch it. It's and they name all the animals, which is enraging, because you're just like, that's not that animal's name. But I don't know. It's like some holdover from the 1960s or something. But the cinematography is great, and there is a fantastic scene where an eagle fails to eat a crab on every level. The crab has complete dominance over the interaction at all times, and puts that eagle in its place. So it's pretty funny.
It should.
As it should, yeah. It's you laugh hysterically. But yeah, so if you want to see what life is like on my island, go watch Seawolf, the island of the Sea Wolves. Anyway,
excellent.
we have wolves that just live on or beside the ocean. Everything they get
awesome.
from the ocean. Yeah,
I can see that. I've like had dogs that were spectacular hunters. Like, I had a dog, Leah, that it was just wild to watch, because she'd stand in the shallows and she'd pick her paws up very slowly so they barely moved the water, put them down very slowly, and then you just see her head go under the water and she'd come out chewing a minnow.
So we should let people know that you are about to throw a monkey wrench into everybody's plans, which is why we're not jumping right into the show.
Yeah.
This is not going to be a normal show, and we're not going to talk about spaghettification today.
So the title of the show was Silly Calculations. What did it get turned into?
Spaghettification.
The title was supposed to be Silly Science Calculations.
Well, it's not.
Okay, so the original title for the show, and I'm going to double check that I'm not lying, the original title for the show was supposed to be Silly Science Calculations, which was something that Fraser had put on one of the suggested show lists at one point, and I was like, yes, that sounds like fun. Let's do that during CosmoQuesticon. And
hard.
Yes, it requires a great deal of preparation. And so the idea was brainstorm ahead of time. I don't know why it says spaghettification. It was supposed to be Silly Science Calculations. All right. I think I know what happened. I told Beth, like spaghettification, and the name just got changed along the lines. Okay, we're good. Okay. We're good. We're moving on. So the idea was come up with a whole bunch of wild and wacky things that it would be cool to know the answer to, and then talk about those answers. Like at one point, I was talking with Skylius, and the question came up of just how long would a human be if you spaghettified them? And I don't remember the exact number right now, but it was over 70 light years long. So like a human spaghettified into a one atom string is over 70 light years long for your average human. And so I just take delight in these kinds of crazy things. And so we are going to, during CosmoQuesticon this weekend, and I'm going to pull up the exact time we are going to do this, we're going to record an episode of Astronomy Cast and give you all the solutions to these crazy problems. But right now, we're going to ask you guys to be part of making this episode awesome. And help us come up with all the crazy and wonderful things that we should calculate.
Right. So like normally when we get questions and the questions are going to require calculations, Pamela avoids them.
Yes.
Because like she can't just sit down and perform these calculations on the fly. It takes some time, and is like, you're really watching the sausage get made. But we thought it would be fun to do an episode during CosmoQuest where we do these calculations and run through them. So start suggesting ideas, and I will propose. I've got a bunch already in my brain, so why don't I hit you with them? Now, are you writing them down? Do you want to write them down? How do you want to do this? Okay.
So first of all, let me tell everyone when this is going to be. And this is a ticket holders only event. And we will be providing the video of this and the audio of this like normal out to all of our channels. But the live recording is part of CosmoQuest on the ticket stage. It is going to be at 4:30 p.m. on Sunday. That is Eastern time. It is at 1:30 p.m. Pacific. And if you don't have tickets for CosmoQuest yet, go to cosmoquest.org. It's 2 different stages, a backstage lounge, 42 guests, which is the perfect number.
And so, sorry, which day are we doing this?
Sunday.
This Sunday?
Yeah.
The 23rd. Okay.
Yeah.
Okay. Make sure that I'm there. I'm going over to my dad's place the day before. So, okay.
Okay.
All right.
Are you
ready?
Yeah, I
okay.
Have.
Based on the results from the DART mission, how big of a spacecraft would it have taken to make Dimorphos crash into Didymos? That's my first question.
So Dimorphos is the moon and Didymos is the... Okay.
Yeah. So
I had to work my way there.
Yeah. So if you essentially canceled out the orbital velocity of Dimorphos, it would fall into Didymos.
Yeah.
So how much of a change in velocity would you have to impart to do that? How big of an impact, or how much more massive would Deep Impact have had to be to destroy Dimorphos by making it crash into Didymos?
Okay.
That seems feasible, right?
Yep.
Okay. Next one. Let's say we wanted to terraform Venus. How much of some other mineral would we need to lock away all the carbon dioxide in its atmosphere?
How much?
How many moles of calcium, magnesium, something like that, to lock up all the carbon dioxide in Venus's atmosphere?
So I'm just going to put carbon absorber and ask someone.
Yeah, I mean, calcium, like limes make limestone, or magnesium's another one, right? So there's going to be a certain number of moles of carbon in the atmosphere of Venus, and you're going to need to know maybe this is a chemistry question, but you're going to need to know how much of another element that carbon wants to jump to more than it wants to be part of carbon dioxide.
Okay. That one I may not have enough time to do by this weekend, but I'll look it up.
Sure, yeah. Ulan Kulu says that 2 astronauts are motionless in space 1 meter apart. How long until they bump into each other? But let's make it crazier. Let's have them be a light year apart, and there's nothing else in the universe.
Okay.
2 astronauts 1 light year apart in an empty universe. How long until their gravity makes them collide?
I like that.
Yeah, me too. Ulan Kulu, I hope you're cool with that, because it's such a great question.
I'm going to say
Arjone
meet
asks,
instead of collide.
yeah, assuming they're spherical astronauts. Arjone asks, what is the largest object that could exist in Jupiter's Lagrangian point? So what is the biggest object that could be in the L4 or L5 point? That's a tricky one.
What?
Like, it can remain inside the Lagrange point. Like, Earth can't remain in Jupiter's Lagrange point. The maximum mass of objects in Lagrange points are a function of the planet. Yeah. And so Earth's Lagrange point objects are smaller than Jupiter's Lagrange points.
Yeah.
What is the heaviest gravity that we could launch a rocket from to get a CubeSat into orbit with a starship? Does that question make sense?
I'm trying to figure out what the CubeSat has to do with anything.
So essentially, we're on a super Earth, and it's twice Earth gravity. And so we want to try and launch a satellite into orbit. So now, because gravity is heavier, the payload that we're able to launch into orbit goes down dramatically. Okay. And so if a CubeSat weighs 10 kilograms, what is the heaviest G planet we could be on and still essentially get to orbit with a starship? So we need to run the rocket equation, but substituting the fat value of G.
Yeah. Okay.
Does that make sense?
Yeah, I just don't know if we know enough about Starship yet.
Use a Saturn V if you want. Sure, we can use a Saturn V.
Or a Falcon 9.
Or Falcon, whatever. Yeah.
I'll figure it out.
Right. So if we launched a Falcon 9 from the payload amount is going to come down dramatically.
Yeah.
And it might be that we can't even launch a Falcon 9, but maybe we can launch a Saturn V.
Yeah.
If we can't launch a Saturn V, maybe we can launch a Starship, because the Starship's going to have more thrust than a Saturn V.
Okay. I'm going to add in a couple that I've been wanting to do and I haven't done yet.
Okay.
So I want to figure out how big a telescope would be needed to find Russell's teapot if it was at L2. So say Russell's teapot is like out there waiting to self-destruct on the mirror of JWST.
What if I wanted to read the headline of a newspaper on an alien planet that is 10 light years away?
That's going to be bigger than the solar system. You don't care, do you?
That sounds like
that's not our problem. Okay.
That doesn't sound like a person who just did a calculation. That sounds like a person who made an assumption.
Okay, and it's going to be a world with no atmosphere.
No, it's a space telescope.
Right, but the headline needs to be on a world with no air.
So that we're not getting the distortion of the...
Yeah.
We can ignore the atmospheric distortion.
Okay.
Yeah, so Shadowcatcher Fox is saying, it sounds like the question wants to know, what is the maximum gravity that the current strongest thrust rockets would be able to take to launch a 10 kilogram into orbit?
Yeah.
Yeah, so that's the key, is like, if we had 2 gravity, how much mass could a Saturn V launch into orbit? Paul Dizzy's asking, how close would the moon need to get to the Earth's surface before it breaks up? Would it become a ring, and would it ever get that close? I mean, that's an easy question.
That's a known problem.
That's a Roche limit. Earth.
Yeah.
Roche limit. Moon. It's like 9,000 kilometers, I think.
You are far better at holding specific numbers in your head.
18,000 kilometers. So if the moon got to within 18,000 kilometers, it would break up.
Okay.
Janelle Duncan asks, if music resonates using atmosphere and air, will they sound different on other planets?
Yes, that is a known problem. It's actually really cool.
Is it calculable?
Would
you know how to calculate it?
So the shift in wavelength is totally calculable. I'm just trying to figure out if it's something I have software that I could like shift music with, and I don't think I have the music handy to shift with.
Okay.
That makes me sad.
All right. So, how close to a black hole of some mass, we can figure that out, would you have to be to see some event in the future?
Wait.
So what about like...
I don't...
As you get close to a black hole, time dilation makes the rest of the universe speed up for you.
Mm-hmm.
And so you would see the universe speed up, and you would see events happen. Like the death of the sun.
Okay. Now I'm with you. I thought you were going to like hang out and like get the next election results and come back. And that's just not going to happen.
No, you don't get to come back. No,
okay.
You get close to a black hole and you watch, like, how about the first red dwarf die? That's a tricky...
I like that one.
It's going to die, and then you have to calculate the time dilation that you're going to experience next to the star. Okay, I got another one for you.
Let me.
What altitude?
All right.
Huh?
I was still typing. I'm sorry.
Okay.
Being slow. Okay, go.
What altitude would you have to be for time dilation to balance out perfectly?
With what?
The Earth. So your velocity around the Earth balanced to your mass at the Earth.
You had me and then you lost me with mass. So
the Earth's mass is causing time dilation. It's causing you to experience less time than the rest of the universe. No, the other way around. More time? No, less time. Anyway, when you're close to a massive object, time slows down for you compared to the rest of the universe. And then when you are in orbit around the Earth, you are going fast.
So the question that you're trying to phrase is, what altitude would you need to be at so time dilation from Earth is balanced with the effects from your orbital motion?
Right.
I'm trying to click in the wrong window.
Although I'm pretty sure that answer has been calculated many times before, and it's on the internet. But it'd be a fun one to do.
Yeah.
Yeah.
I like that one.
Okay. Arjun asks, what was the last time sound was audible in the universe?
Ooh.
It's a good question, but I don't know whether you could answer it.
Too hot for anyone to exist.
Well, that is not the question. The question, I guess the point is like sound can only exist when particles are dense enough to transmit the sound.
Yeah.
And so at a certain point, the density of particles in the universe was so low that sound could no longer transmit. So what was that time?
I'm going to see if I can look that up. That's not something I can necessarily calculate.
Well, I guess I would calculate the density of air for sound to propagate. Or minimum.
Here's how you phrase it. At what point did the universe stop being capable of transmitting sound through the distribution of mass?
Yeah. And so at a certain point, the entire universe was a plasma. Yeah. And if you got into it and stuck your head in it, you could listen to the universe.
Yeah.
I wonder if you could hear if there's something in the cosmic microwave background radiation that would let you.
Oh, we totally, so all of the structures we see in
that's
the
what
CMB
the acoustic,
are acoustic. Yeah, those are all acoustic waves.
Yeah.
So yeah, the early universe totally was making noise, and that noise was what resulted in the large-scale structure we see today.
Yeah. And so how long after the CMB would that sound still be there? It's a great question.
Yeah. Yeah. So Cosmic Seekin over on Twitch is saying, you can't see an event in the future as the speed of light prevents it. So what we're saying instead is, like, I as a human being normally could not live long enough to see the very first red dwarf that ever formed in our universe die, because the universe will be like 1 trillion years old when that happens. But if I'm in orbit around a black hole, my ticking clock slows down relative to the clock that is determining the age of that red dwarf. And so the question is, how much do I need to slow my clock so that in the normal length of a human life, I still get to see that red dwarf die?
Yeah.
I'm extending my life to increase the amount of death I might see, which is morbid, but it's Halloween.
Yep. How much solar power could you get from starlight?
Yeah. Yeah.
Like if you're far away from the sun, how much solar power could you gather from the universe?
So I'm going to make this simple. I'm going to say in the darkness of space on the wrong side of a coronagraph, or the right side. Because otherwise I have to get into how far away are the nearest stars.
Well, I mean, you could just say like average distance. You're the average distance of any of a star in the Milky Way. You are 4 light years away from the closest star.
I think it's 2 light years, because if the average separation between stars is 4 light years and you're trying to get away from things, they're going to be 2 light years away from you, because otherwise you're at a star.
Yeah.
Okay, so I'm going to phrase it as how much energy would be hitting a solar panel, and then it's the efficiency of the solar panel is how much energy gets produced. And I am misspelling everything. This is where you learn that my camera is in front of my monitor.
Paul Disney is asking, how long would it take for me to reach the edge of the observable universe in a ship that accelerates at a constant 1G for half the trip and turns around and decelerates at 1G for the latter half?
There's no edge to the universe or edge to the observable
Edge of the
universe?
observable universe, yeah.
Okay, that
yeah.
I'm willing to go with.
Yeah, I've done that calculation. About 10. Well, you would experience. I mean, you would go. How? I guess the question is, you'd be like 40, I think.
You'd be what?
40.
Okay.
You would experience 40
I was very
years. Yeah,
confused.
you'd experience like 40 years if your spacecraft was constantly accelerating at 1G, and you would be traveling for 46 billion light years. 42? 46. 46. Yeah.
Did you figure out like all of the current edge of the universe is moving away from you as you go kind of?
Yeah, so I wasn't adding the continued expansion of the universe.
Okay.
I'm saying you're traveling 46 billion light years distance. And so the place that you're trying to get to is no longer there.
Right. It is
because
moved.
I didn't. But I mean, if you want to do it, I mean, we don't know what dark energy is going to do.
A problem for in the future, but I'll see what I can do.
Yeah. How big will the observable universe be? Because it's almost bordering on calculus, right? Because the universe is getting bigger the longer you travel.
Yeah, it's totally a calculus problem.
Yeah, yeah. And so the answer is going to be, yeah.
I'm going to do, and that should have been G, not C. So if you're constantly accelerating and decelerating at G, at some point along there, you're going to exceed the speed of light.
No, you can't. So what happens is you just experience more time dilation.
Yeah, fuck. Okay.
So obviously you need an infinite amount of energy, but you're going 99.999999999. You just get closer and closer to C, but you never actually reach it. But as you do, every 9 that you tack on the end makes you experience more time dilation.
Okay, I'm gonna first try to do a simplified version of that, which is traveling at a constant 80% the speed of light.
Because then you're experiencing thousands of years, well, billions of years. One thing, it's a Lorentz function. Let's see.
Yeah, there's a lot of Lorentz functions involved. The issue is that you have to include the relativistic version of the expansion of the universe equation, and the idea of trying to set equal the relativistic expansion rate and the equation for motion that has half of it accelerating and half of it decelerating is awful.
Here, try this. I'm going to put this into Slack for you.
Okay.
So you accelerate at 1G. Your starship mass is 10 tons, 1 ton, 1 knot. Your destination is, you can pick the distance. So I'm going to say it's 10 light years away. You can arrive at full speed.
Right, but this isn't including the acceleration of the universe, is it?
No, that's the separate. So that's the separate piece. This is what gets you. You experience 4.8 years, and you've traveled, but it's 11 years on Earth, and you've reached 0.98 C.
Mm-hmm.
And so then you can kind of take it to the next level. You can go. The distance is 1 billion light years.
And this is where we're both simplifying it in different directions. I was looking to simplify it in terms of, let's just have constant velocity. And you were simplifying it in terms of, let's ignore the expansion of the universe.
I'm saying constant acceleration. I'm saying just use constant acceleration as opposed to constant velocity. So yeah, there's an app. I'll put this into if everyone wants to play around with this, I'll put it into the chat. So I put in 1g acceleration. I made the starship mass 1 ton. I made the destination, the distance as 100 million light years. So let's do 10 billion light years. Okay. So you experience 44 years on the spaceship. Earth experiences 10 billion years, because that's sort of the magic of you traveling at going 10 billion light years. And you need a ludicrous amount of fuel.
Yeah.
And that's allowing you to stop. And so
I'm just going to overshoot because I'm going at a constant acceleration, and I go bye-bye as I fly.
Well, but this is the question, right? The question was, if you wanted to stop, arrive at the destination and stop, then you go half the speed, half the distance at one rate, and then half the distance the other rate. And then what you would want to do is you'd want to calculate the size of the universe at this point. So that's the challenge.
I think this one's going to end up becoming an entire episode at some point, so we can discuss all the fine points of it.
Right. Yeah.
It's like a graduate level relativity problem.
Play with the calculator. It's super fun and lets you mess around with different. Like the part that's mind blowing is that you're experiencing 1g of gravity. Mm-hmm. So you are experiencing normal gravity for the entire journey. Mm-hmm. And yet. And you have only, in a human lifetime, you have gone 10 billion light years away. And I can make that, if I go 100 billion light years, I'm only 49 years old. If I go 1 trillion light years, I'm only 53 years old. 10 trillion, 58. 100 trillion, now I'm 62.
So you're assuming that you were born and placed as a newborn onto the spacecraft, which is going to care for your every need and educate you as you are journeying out to this point.
Yeah.
All by your lonesome.
Yeah.
Okay. Just making sure.
Yeah,
and I'm realizing everyone sees my shirt saying I hate, and that didn't help. It says I hate everyone and pants. Because sometimes you just need to hate everything in pants. I just wanted to explain that because when that's all that appears on camera.
That's a good question. Ulinkula asks, how much would a 1 millimeter hole in the International Space Station deplete the air enough to render the inhabitants unconscious?
Oh. Okay, they would hopefully, yeah.
You need to have the pressure. You need to know how quickly the air is going to go out. A 1 millimeter hole, the pressure of the space station versus it. Again, as the pressure gets lower, the rate is going to decrease. And then what is the amount of minimum air pressure? Paul, I put the calculator just a little up in the chat there.
Okay. You were thinking hard with your tongue sticking out.
Yeah. Okay. So what about when will, like, something about the cosmic microwave background shifting to like radio waves that are a light year across?
Because it's currently microwave, so it's going to become radio. How about until it's like your favorite radio stations, like 103.5?
That's awesome.
Yeah.
That sounds great. Yeah. When could you listen to the universe on a radio, on your radio? Arjun is asking, how long until the Voyager is just an unrecognizable ball? It's about 1 billion years. The record actually should last about 1 billion years.
Okay. So for those of you who tuned in late and don't know what it is you're experiencing, this weekend is going to be the CosmoQuest celebration of science and creativity. We're going to have events both in a private Discord server and on twitch.tv/CosmoQuestX. One of the events for ticket holders only is going to be a recording of Astronomy Cast that we will post later to all of you, in which we're going to discuss all sorts of silly science calculations, and we're brainstorming the kinds of calculations that are going to make it into the show. And we're doing that right now. So I'm just filling things into a Google document. I will calculate things in order of what can I do the quickest so that we can get the most things into the show. Yeah. And I will eventually chew through all of these lovely things later. One thing that I'm going to throw in, this is a calculation I've already done, but I think it is worth bringing up. And this is how big a difference is there between what Superman can see with his normal vision and his X-ray vision. So like X-rays are much, much smaller, which means he can see a significantly higher resolution, but just how much higher of a resolution?
That's interesting. How do you have a spaghettification question? Like, but it's horrific. I'm like wondering, how close would you have to be to a black hole before you are the spaghetti in a spaghetti dish? If it's spaghettification, when are you actually spaghetti? That's too horrific.
I was just going to figure out how long a human being would be. Rerun my maths.
Like the same thickness as spaghetti.
It doesn't work that way, though.
No, I know. You're broken up into pieces. But when are the pieces as thick as spaghetti? Commentary Fairy says, separate calculation for angel hair. How high did a dinosaur fly during the Chicxulub event?
Let's do how fast, because that's more.
Sure.
Or let's go, greatest distance, I think. I'm trying to figure out. I want to do a conservation of energy. So if I know the velocity they exited the surface of the planet with, which you can get from the shockwave, then by figuring out where all of the kinetic energy becomes gravitational potential energy, that gets you the distance they can go if they go straight away.
Yeah. Arjun asks, how big an object would I have to be on to launch myself into orbit? So why don't we change that? Like what it would be if I just wanted to be an astronaut. What's the smallest rocket to be an astronaut?
Why smallest rocket? Do you mean like least
So
amount of?
you're climbing into a rocket fairing, and you're going to orbit.
Okay. So that's in terms of like the amount of fuel that needs to be behind your butt.
Yeah, yeah. Like
Okay.
how like when we think about a Saturn, we think about a Saturn V, we think about a Falcon 9. Falcon 9 is carrying several tons to orbit.
Yeah.
But what if you just wanted to carry 200 pounds to orbit? Right. How small of a rocket would that be?
I'm going to do
I mean, it would
human
kind
plus
of be. Look at,
spacesuit plus
yeah,
tank of O2.
like oxygen. Yeah.
O2.
I mean, rocket labs are designed to launch 300 kilogram payloads.
Yeah, so they could probably
So
do it.
so
I
it's
just
kind
don't
of
know
that.
what
It would be a
volume
rocket
they
lab.
expect that to be in.
Yeah.
Because there's the
Let's see what the rocket lab fairing size is.
yeah. I'm like imagining fetal shaped an astronaut in the fetal position here.
1.2 meters in diameter and 2.5 meters in length. You could
Okay, so you
just
could
sit
stand
right
up.
inside of it.
Yeah.
Yeah.
Okay.
Yeah. And the Electron would be mass payload to low Earth orbit is 300 kilograms. So it would be smaller than an Electron.
So here
Like
we're imagining I'm going to add a parachute. Like so you've read John Scalzi's Old Man's War?
Mm-hmm.
So like in both Old Man's War and then The Expanse also had a similar idea to this, I think. There's the idea of a spacesuit that you can jump through an atmosphere in and then end up basically being as a very toasty but still alive thing as you open your parachute low enough.
Yeah. I finished reading Termination Shock, which is the new Neil Stephenson book.
I haven't read that yet. How is it?
It was great. I loved it.
Okay.
But I've never read a book by Neil Stephenson that I didn't love. And so at one point, people are getting attacked by Mars rover landing systems. By soldiers being carried by sky cranes.
Okay, that makes more sense. I was imagining like our happy little satellites decided that they were going to like gain intelligence and I just realized
so
I've been typing in a window no one could see the entire time. I just fixed
So
that.
they are launched in suborbital rockets.
Yeah.
And then they are deployed on sky cranes to their destination.
Itty bitty little tiny sky cranes.
Mm-hmm. Well, I mean, sky crane carries, say, 4 soldiers, 6 soldiers.
So normal sized sky cranes.
Yeah. And so you get launched, you then deploy, you pops the parachute, or has the heat cone, pops the parachute, then floats down and deploys the sky crane and lands and literally just stops, and the soldiers just are standing on the ground.
Yeah.
And then the sky crane flies off.
That's wild.
Yeah, it's really cool. Yeah, there's a bunch of ideas like that in the book. How about a TIE fighter ion engine?
Yeah, that one's fun.
So TIE fighters, right? They have twin ion engines.
Yeah.
So how how much bigger would they have to be? How light is the TIE fighter for them to work the way they do? Because they're ridiculous.
Yeah.
So I'm not sure what the question would be, but you could take the thrust of a TIE fighter and thrust of an ion engine and try and calculate it.
So are you watching Andor?
Mm-hmm.
So we know from Andor that they're able to get TIE fighters can like escape a planet's gravity. So let's figure out just what would it take for twin ion engines on a TIE fighter to be able to go from.
So we could know the mass of a TIE fighter.
Hooks.
We could know the size of the ion engine exhaust, and the calculator would be like how many times more powerful is a TIE fighter than our best ion engine today. Yeah.
So yeah, I'm assuming they're starting from their weird meat hooks and then just escaping Earth's gravity.
Mm-hmm. Cool.
I saw how they like have them taking off, and like I wouldn't have imagined that you could successfully have spacecraft that require meat hooks, except we're using chopsticks for Starship, so I guess a future of spacecraft that require like being caught by hooks is actually something we can imagine.
Right. Okay.
And there were no plot at all spoilers in my randomness there. Just knowledge that there are meat hooks involved in the launch of TIE fighters. Not real meat hooks. Spacecraft hooks.
Little clampies. Clampies.
I think we are coming up on the top of the hour, and this is more than enough questions.
I'm sure it is.
This is going to keep me blogging for quite some time after, I suspect.
I'm just getting started. We do this all day.
All right, so all of you who want to watch this go down live, go get your tickets. It's not just Fraser and I. There's going to be, we have Seth Lockman from Blue Shift Aerospace, Yov Landsman. I forgot the name of his new aerospace company. We have some NASA folks coming. There's all the creativity you could ask for. It's going to be amazing. And let me just read off some of the sessions. These are all going to get posted later today. So we're going to do a discussion about robots and the uncanny valley and why TV shows like the new Megan that came out are just so decidedly creepy. We're going to do fact-checked music of the cosmos, looking at various lyrics about space and whether they're right or wrong.
That's awesome.
We're gonna do a session talking about Kerbal Spaceflight. Learning a game in which learning is a game in which only the Kerbals die is the current title. We're gonna do rocks in space, talking about all those little rocks that we're sending spacecraft out to and what we can learn. How do we get to space? Let me count the ways. So cool and yet so terrible is a look at this future of daily launches of massive rockets and all the consequences and coolness that comes out of it. Discussion on androids. Is this how we get Cylons? We have musical guests Mary Amber, Christy Cates, Andy Rivkin. DJ David Joseph Wesley, of course, is going to be with us. as one of our guests of honor. So go get your tickets, and let's just spend the weekend talking science and creativity. Sound good?
Sounds good.
Okay.
Yeah. All right. All right. Well, thank you everybody for tolerating hanging out with us as we brainstorm. Although, it might be good. Like, people are saying they kind of enjoyed this. It might be fun, like, when we figure out what the topics are going to be for future seasons
on stream.
We'll do that on stream, so people can see how our thought process works and be a part of it if people want to see that. That would be fun. All right. Well, thank you everyone for hanging out with us today. Really appreciate it. Thanks to everyone who watches us on YouTube and on Twitch. Thanks to all the moderators. And we will see all of you on Sunday.
Yes. Sunday
all right.
at 1:30 Pacific, 4:30 Eastern on the Discord stage.
Right on. Okay. Thanks, everyone. See you later.
Bye-bye.